so it's my pleasure to announce the second speaker of this afternoon. He's the physics part, even more physics. And yeah, so André Assis is speaking about Weber electrodynamics, and today he starts with Ampere.
Good afternoon, everybody. In the first place, I wish to thank Joa Weber for organizing this advanced school. It's a great opportunity for physicists and mathematicians to get together. And I'm especially happy because it was Joa Weber, because I will talk tomorrow and the other days about Weber's electrodynamics. So I guess maybe he may be a descendant for the great Weber family, which had many professors and scholars in Göttingen and in different universities in Germany. So maybe, who knows? So maybe it's not a coincidence, so I'm very happy. What I will talk with you today and the other days during the school is some more physical aspects of these topics, which even for physicists, normally they are not known. Everyone knows about the name Ampere, but what we will present here may be new to many of you. I will talk especially about this book, Ampere's Electrodynamics, and it will circulate it was a book with myself and Jean-Paul Chaib. He is here, the co-author of this book, and we did work together for 6 years on this project, so it is circulating with you the English and the Portuguese versions. The English version is available in PDF in my homepage. You can download it there for free. And I will also talk briefly of another book, which is Inductance and Force Calculations in Electrical Circuits. It also has a Portuguese version. This one, only the Portuguese version is available in PDF free of charge in my homepage. But I will discuss these two here. So at the end, please return the books here. This book in particular, I call your attention because also we speak a lot about Ampere. For 200 years he was not translated, not even to English, his works, only portions of it. So the work with Jean-Paul Chaib, we made the first complete translation of Ampere's main book. We first translated it to Portuguese, 2009, and then we made a new translation to English, a complete and commented translation. So maybe this is one of the reasons why his work is not so well known. 200 years ago, everyone could read French. Nowadays, it's not the same. So how did, let me present you at Ampere 200 years ago. He and the others, they knew about Newton's law of gravitation, 1 over r squared, which Kai told us just ago. He knew about Coulomb's law for electric charge. It's similar. This is proportional. Force proportional to the product of the charge and 1 over r squared. Here we can have positive and negative. And Coulomb also make experiments with magnets and arrived at a similar equation for magnetic poles. We usually don't see it in the textbooks, but he wrote a similar equation for magnetic poles, north and south magnetic poles, also 1 over r squared. So 40 years later came Ampere with a force between current elements. It's also proportional. I1, I2, the intensities of the two currents, falls as 1 over r squared, is a central force just like this, but it is much more complex because it depends on 3 angles, alpha, beta, and epsilon, which I will show later on. They are related with the angle between each of the current elements and the straight line connecting them. and epsilon is the angle between the two current elements, okay? So it's much more complex than the other force laws. So how could Ampere arrive at such an equation? I will just give you some ideas, because I cannot in 1 hour talk about 500-page book, but I will give you an idea of what he did. So it's exactly 200 years ago, this year, Oersted made a very famous experiment. He did have, let's suppose this is a magnetized needle. It points along, let's say, the north-south. Then he put a current carry wire below or above. Let's suppose that the magnet is above the current carry wire. When there is a current flowing, he observed that the compass needle did turn by an angle. When it put it below, it did turn to the opposite direction. Okay? So, when the compass needle was above, no current, it was pointing along the magnetic north-south direction, which we call magnetic meridian. When there is a current, the north extremity of the compass moves towards the east. When the compass needle is below the current, it moves towards the west. Okay? This was the observation by Oersted, showing for the first time a connection between electricity and magnetism, or more specifically, between magnetism and a current carrying wire. Okay? First time in history. How did Oersted himself interpret these experimental findings? Oersted believed that here we have the wire carrying a current, and the compass needle went towards the east, west. Okay? So Oersted did believe that there were charges moving not only inside the wire, positive and negative in opposite direction, but he believed that outside the wire there were charges, electric charges, describing elliptical orbits around the wire. And in his words, the negative charges flowing in this elliptical orbit would propel the north pole of the needle, just like a wind, but a charge pressing a magnetic pole. And this negative charge would not act on the south pole. The positive charge flowing outside the wire, on the other hand, would press the south pole, but it would not act on the north pole. This is very strange, but that was Oersted's own interpretation of his own findings. Other scientists had different interpretations. For instance, Biot and Savart, two French scientists, they believed that when you have, now the current is here, if the magnet begins like that, it will make like that. So he believed there was a torque here, and how could that torque originate? So Biot and Savart believed that the wire did become magnetized. And in particular, as the needle outside becomes orthogonal to the direction of the wire, so these would be small magnets around the periphery of the wire. If there is a current flowing here, there would be extremely tiny magnets on the surface of the current carrying wire. And these magnets would make this one make like that. So that was the idea of Biot and Savart, that the wire became magnetic when a current flows through the wire. Faraday himself was interested in this problem, and Faraday had a different interpretation. So suppose we have a current here, and we have a north pole here. So Faraday believed that Oersteds experiment did show a transverse force between the current carrying wire and the north magnetic pole, and the south pole would be pressed downwards. This explanation by Faraday creates a problem because it creates an internal or primitive couple or torque. The system would begin to turn by itself. But that was Faraday, how he did interpret Oersted. You see, each one had a different interpretation. How did Ampère react to this discovery? When Oersted made his experiment, Ampère was 45 years old. He was a mature scientist. Normally, the great scientists, they made their great discovery when they are in their 20s or between 20 and 30 years old. But Ampère was 45 years old. He was completely amazed by that discovery by Oersted. This comes from a letter which he wrote to his son as soon as he discovered about the discovery. I regret for not sending this letter 3 days ago, but all my time has been taken up by an important circumstance in my life. It changed Ampère's life. Ever since I heard for the first time about the discovery by Mr. Oersted, professor at Copenhagen, of the action of galvanic currents on the magnetized needle, I have been thinking continuously on this subject. And the only thing I have been doing is to write a great theory about this phenomenon and about all those phenomena already known about the magnet, and to perform experiments suggested by this theory, all of which have been successful and made me know several new facts. So this was a decisive moment in Ampère. Before 45 years old, he had not worked with electrodynamics. He worked only for 7 years. Then he stopped and went to philosophy of science. He didn't return after 7 years. The whole of Ampère's great work was from 45 to 52 years old. What was his idea? Completely different from Oersted, completely different from Biot and from Faraday. He made two assumptions. One, he assumed the existence of forces of attraction and repulsion between current-carrying conductors. No one had seen these phenomena before. Moreover, he assumed that there were electric currents inside magnets and inside the Earth. So according to Ampère, this deflection observed by Oersted was not due because the wire did become magnetized, but because there were currents inside the magnet, and these currents were interacting with the current in the wire. It was a direct interaction between currents, no magnetic poles. Completely different paradigm. But this paradigm has been extremely fruitful. So that was his original idea. So this led to a full research program. This research program, he then tried to model electrodynamically with currents any phenomena about magnetism without utilizing magnets, only current-carrying wires. That was one part of his program. The second part was to try to find the force between two current elements. Okay? So I will try to show some steps in this research program, which he was very successful. In 7 years he could succeed. The first thing which Ampère wanted to explain with current was the fact that if I have two magnets, they attract if they are aligned, or they repel. Okay, so he wanted to show the attraction and repulsion between two magnets, but with currents, not with magnets. He wanted to model a magnet as some kind of current. So this was his first experiment, which he described in his papers. He knew that two magnets, as I said, they attract one another. He then replaced one of the magnets by a spiral, current-carrying spiral. It was connected to a source of current somewhere else, a pile, and it did generate a current. When there was no current, these two were vertical. When a current was passing through here, they attract each other. If he did change the direction of the current here, they would repel one another. So this was the first idea. He did model a magnet as a spiral. He then changed the second magnet, and then he found for the first time in history interaction between two current-carrying wires. If he did change the direction of one of them, they repel. These are his words. It was in this way that I discovered that two electric currents attract each other when they flow in the same direction and repel each other in the other case. I myself have repeated this experiment didactically, and very interesting one. Okay? So it was in this way that he discovered this idea that two currents in the same direction attract and opposite direction repel. So this was his idea. So he wanted to show the repulsion or attraction between two magnets, but working only with currents, and he did succeed. If a magnet was a current flowing in a spiral. Okay? So as a consequence of this discovery here, he made his most important, most famous experiment, which every textbook or science laboratory has this experiment, which is this current balance experiment. So then Ampere performed his most famous experiment showing the attraction and repulsion between two parallel straight wires carrying steady currents. This device is the basis of the current balances available in all didactic physics laboratories. So these two lower portions here, they are at the same horizontal plane. This one is fixed. This one can turn around this axis. So it can turn here just like a pendulum. This is just a support, the current comes here, and here's the fixed one. So when they are at let's say 5 centimeters apart. When the current flows in the same direction, they approach each other. When he reverts one of the current, it moves away. Okay? First he found that in spiral. Then he made this device. This is his most important, most famous experiment. But then he did go on. For instance, what we know since the Chinese, more than 2,000 years ago, that if I have a magnetized needle, which can turn around a pin, if I release it in any position, it will point in a certain direction. This direction is called the magnetic meridian. Let's suppose that it is parallel to this direction here. So this is the magnetic north-south direction, okay? I leave the needle here, it turns and then stops here. So this is the north-south magnetic direction. Ampere wanted to repeat these with currents. He then made a loop. It could be circular, rectangular, any shape. And this loop was connected to a battery. There was no current, it put in any direction. When you let the current flow through this circuit, and it can turn around the central axis. When it stops, if you put it in any direction, when you put the current, it will oscillate and it will stop orthogonal to the needle. Okay? So this was the analogous to a compass needle, but utilizing a current carrying wire. Okay? You do the experiment here without any kind of magnet nearby. You just let it here. When a current flows through this, it will turn and it will stop in this direction. Okay? Orthogonal to the magnetic meridian, orthogonal to the north-south direction of the earth. So he did succeed in another famous phenomenon of magnetism. So when you let the current move, it will become orthogonal to the direction of the magnetic meridian. Let me move on. In order to arrive at his force law between current elements, Ampère was a brilliant scientist, a brilliant mathematician, and a brilliant physicist. And he introduced a whole new method in physics, which is called the null or zero method in physics. A mobile circuit is placed between two other circuits. And this mobile circuit can move to the right or to the left, or it can turn. And then Ampère looks for certain configurations in which equilibrium takes place, in which the central circuit, although it is free to move, it does not move. Very little resistance. It could move, but it doesn't. From these phenomena that it does not move in these specific configurations, he could deduce his force law. I will show you an idea of how he did that. It is a brilliant thing which he did. In his 7 years, Ampère made thousands of experiments, but he never made a single experiment in which, for instance, there was a current flowing in the wire and another here, and he did change the distance, and he made a table with the position of the other as a function of the distance, or as a function of the angle, or as a function of the current intensity. He never made experiments with number, as every physicist does. He only made experiments which yielded zero value. He did make no numerical tables. It's amazing. Let me show to you how he did that. For instance, how did Ampère discover that the force between current elements falls as 1 over r squared? He believed that, but he made a very fascinating experiment which showed that. His force law, as I showed to you, it's analogous to Newton's law. I1, I2, function of the angles, but he assumed that it falls as r to the nth power. Okay? Then, suppose this is an ideal situation, just to simplify. I have 3 pieces of wire carrying the same current in the 3 of them. The left and the right one, they are fixed in the laboratory. This one can move to the left or to the right. Okay? This has a size L, 3L and 9L. This distance is R and this is 3R. If I look at these two and these two, if I shrink 3 times, I come back to this one. So it is completely similar. All the angles between the extremities, they are the same, and so on and so on and so on. So if the force was 1 over r squared, this one would be at rest. If the n was smaller than 2, the force, these two attract. The force here will be essentially, because it is proportional to the length. So it will be L times 3L divided by R to the n. The force to the right here, acting on this one, will be 3L times 9L divided by the distance, 3R to the n. So if the n is equal to 2, so we will have 9R squared. 9 followed is R, 3L squared over R squared. 3L squared over R squared. So if n is 2, this one will be at rest. If n is smaller than 2, it will move to the right. If n is greater than 2, it will move to the left. Okay? But this is not a real experiment, because these are open circuits. We need to make experiments with closed circuits, but this is the main idea. Okay? The real experiment is this one here. So we have 3 circuits, radius R, 3R, 9R. Distance, small r or d, 3 small r or 3d. And this one can move to the left or to the right. In this case, this repels this one, and this repels this one. So it is repelled by both of them. This is a real experiment. So when we do the experiments, although it is free to move, it doesn't move. So the force must be 1 over r squared. It cannot be 1 over r or 1 over r cubed. Okay, it's an experiment, fascinating experiment. Okay, so this was one of his experiments with Null method in physics. No measurements, just observation. When does it could move but doesn't? And from these he so with experiments of that kind, he arrived at this expression. I won't go into details because there are many subtleties, okay? But this is his final expression. So I1, I2 over R squared, proportional to the length of the 2 elements and depends on the angles. Either alpha, beta, and epsilon. Alpha is the angle of one of the elements with the straight line connecting them. Beta is the other angle. Epsilon is the angle between the 2 current elements. Or, alternatively, in terms of another angle, gamma, which is the planes formed by the 2 current elements and the straight line connecting them. In this first expression here in particular, Ampère, from the beginning, he making the composition of his force along the directions of the elements and so on, he knew that it would be proportional to the sine of alpha, sine of beta, cosine of gamma, but he believed this last term here was 0. It was a surprise for him when 2 years later he discovered this minus 1/2 here. In particular, if this here was 0, alpha and beta are the angles of each element and the straight line connecting them. So that if they are aligned along a straight line, if there is no this component, there should be no force between 2 currents which along the same straight line. But then he did realize that the complete formula is this one. Then this means that 2 current elements which are like that should repel one another. It was a complete surprise for Ampère. He didn't, in the beginning he believed there was no such component, but in the end he found that. I will discuss the consequence of this.
How did you reach that this term exists?
Because of these Null method, different experiments and so on and so on and so on.
So he did measure such a longitudinal.
No, that comes later.
Force.
That comes later. To arrive at 1/2, he utilized only the 0 method. But then he concluded that this is -2, 1/2, and there is some consequence which I will discuss in a minute. So this is the expression of Ampère in the usual international system of units, MKSA. Okay, this vector notation, mu naught, epsilon naught, currents in amperes, force in newtons, and so on and so on and so on. Let me show, so this is the essence of Ampere's force law. This expression does not appear in any textbook in physics. It's completely gone for 100 years. Let me show you another of these Null experiments, which Ampere also devised. He has this, the real experiment. This arch here can move. Here we have a mercury trough, so it is conducting. And this arch can move clockwise or anti-clockwise. And then he did have a closed circuit of arbitrary shape. And also this arch was free to move clockwise or anti-clockwise. It didn't move. So Ampere concluded experimentally that the force on a current element is always orthogonal to the current element, no matter the shape of the closed circuit acting on it. This was an experimental result, but Ampere also showed mathematically from his complete force law, when he did integrate this expression here, Ampere didn't utilize vector notations, so he didn't have cross products and so on, but his expression for us to understand is analogous to this one. So his force after integration of a circuit of arbitrary shape acting on an external current element, which will be always orthogonal to the current element, no matter the direction of this, because the vector product is always orthogonal to this. Okay? This is a theoretical result, but first he had made the experiment, shown that although it could move, it didn't move. But then he did integrate his force law and obtain this expression. So these were results by Ampere. Now I will go to the expression which we find in the textbooks, because this of Ampere disappeared. It's not to find in any textbook. The only thing which we find in all textbooks all over the world is the expression by Grassman, a German mathematician. This Grassman, 20 years after Ampere, he, as I said, the most famous experiment by Ampere, two currents in the same direction attract one another. And he concluded that if they are along the same direction, they repel one another. So if I make them moving around the circuit, there will be a certain angle when it goes to zero. Maximal attraction, attraction decrease, there is zero. When this angle is around 35 degrees, then begins repulsion and maximal repulsion. Okay? This is a property of Ampere's law. Grassman, he said in his paper that he didn't like this property. To him it was... And then he did create another force law. Without a single experiment. At least he never published any experiment. Never said he made any experiment. What he did do essentially, Ampere had shown that when you integrate his force law, you obtain this expression here. Only for integrated force of a closed circuit acting on an external current element. So Grassman essentially said that even for two current elements, the force will be this one. Even for two current elements. Essentially he said that the result which was valid when you integrate, you can drop this integral and say that this is the expression. Okay, that's what Grassman did essentially. Okay, so because this expression here does not have this property that the force goes to zero at 35 degrees. Okay, and when you integrate that, you obtain the same as Ampere. Okay. Let me show you. So, these are the two expressions. This is the Ampere, and this is the one which appears in all physics textbooks. IDL cross dB, where dB is the magnetic field given by Biot, Savart, and so on and so on. And when we open these two double cross products, we obtain this here. I will compare this with this one. Minus mu naught over 4 pi, I1 A2 over R squared, the same. But here we have 2 dl1 dl2r. Here we have 1 dl1 dl2r. So there is a 2 here which is not here. And the last component is completely different. In particular, this one from Ampere is central. Points along the direction which connects the two elements. This one from Grassman, this one from Grassman is not, because it points along the direction of one of the current elements. So they are completely different. But the only one which we find in the textbooks is this one. How can it be that we keep only this one and forget about Ampere?
Yes, I'm confused with the first one, because you said the force is transverse is perpendicular, right? The element of current.
When you integrate.
But only when you integrate.
Only when you integrate, not for two current elements. But if you integrate a closed circuit, no matter the shape, then the force will be orthogonal. Only after you integrate, but not for two current elements. For Ampere. For Grassman it will be for two current elements, but not for Ampere. Good point. So, how can we forget about Ampere and keep only Grassman? Because they have exactly this property. When you integrate both of them, the force of a closed circuit acting on an external element, they are the same. Ampere is equal Grassman, which is this. When you integrate, if you have two or more closed circuits, you cannot distinguish them. Okay? But are there differences? Yes, there are. In particular, suppose that I have two current elements like that. According to Ampere, they do not act on one another. 1 on 2 do not act, and 2 in 1 and 1 on 2, they do not act on one another according to Ampere. According to Grassman, it's very curious. This one exerts an upward force in this one, but this one does not react back on that one. That's what Grassman got. And that is what we all learn in the textbooks. You see, there is no action and reaction. That's even worse than that case with Faraday, because with Faraday there was action and reaction. Not along the same line, but there was an internal torque, but here there is even a net force of the system on itself. Very strange. Another distinction, as I said to you, suppose that I have two current elements which are aligned along the same straight line. According to Grassman, they do not exert force on one another. According to Ampere, they repel one another. As I told you, he first found that theoretically, that they should repel. He was surprised with the result. He didn't expect that. Ampere was so surprised with this result that he did create a new experiment to test this property of his force law, even before knowing about Grassman. Okay? He was so surprised with this repulsion that he did create an experiment to see if it was real or not. This experiment is known as Ampere's bridge experiment, or Ampere's hairpin experiment. I will show it to you. So we have here a battery, we have here two mercury troughs, and we have here a bridge. B, C, D, E, F is a bridge, a conducting bridge, which can move. It's floating in mercury. So when there is no current, it is stationary. When you close the circuit, and there is a constant current, no matter the direction, clockwise or anti-clockwise, the bridge moves to the right. So there is a force acting here. So this is the experiment. According to Ampere, this motion of the bridge to the right is due to the longitudinal repulsion between AB and BC, and the longitudinal repulsion between EF and FG. Okay? These repulsions here and these repulsions here will propel the bridge to the right. According to Grassman, there is no such force. So in principle, you could not explain this experiment. But there is a way out, even for Grassman. If you consider the force that the bridge makes on itself, with Ampere that goes to zero because of action and reaction. But Grassman does not satisfy action and reaction. But if you consider the force exerted by the external circuit on the bridge and the force of the bridge on itself with Grassman, then you obtain the same as Ampere. So very strange result, but that's the way out to explain it. But this is a very famous. Ampere created this experiment to test that longitudinal force. He was so surprised, he didn't believe it in the beginning. So he made this experiment with Arago, and then he could find the effects. Another experiment, which I was telling you during lunchtime, which is, for instance, I worked with this Peter Granoux in Boston, MIT, almost 20 years ago. Neil Granoux is his son, who works in Oxford. So here we have a circuit, a capacitor bank, a switch. Here we have air, and here we have a thin wire. Here we have a thick wire. When we close the switch, we have a capacitor bank here. We create sparks here, and the current begins to flow. When the current begins to flow, the thin wire breaks into many pieces. It explodes, literally. These are real pictures of the wire. It breaks in 1 millimeter length pieces. Okay? So Peter and Neil Granoux, they explain this breaking of the wire as due to this longitudinal repulsion here of two current elements which are aligned with one another. This phenomena has been known for more than a century. When you have in your home, to safety, you have this, when you have a blitz, it breaks a wire and the current doesn't go to your home and your equipment is safe. So they utilize this phenomenon. The explanation, which is being discussed for 200 years, no one knows the correct answer. Peter and Neil Granoux give this explanation. People sometimes said that it was due to Joule heating, because it's a huge current, mega amps for a very short time, but it could melt and so on. And then they did make analysis of the cross-section. It showed that it was broken in solid state, not due to melting, but due to mechanical tension, okay, and so on and so on and so on. So these are just two recent, old and recent experiments which are being revived nowadays. So this guy Tricker, he was one who wrote a book, Early Electrodynamics, 1965, with a partial English translation of Ampere's work. These are the words by Tricker in this book. In the theory of gravitation, Newton was already provided with a knowledge of a range of the phenomena, mainly through the medium of Kepler's laws, which Kai told us today. Ampere, on the other hand, had to discover the laws as well as provide the theory, and thus do the work of Tycho Brahe, Kepler, and Newton rolled into one. That is Tricker, who works with the modern field theory. Maxwell in his treatise, Maxwell knew not only Ampere's force, but also Grassman's force, which I told you today. In article 527 of his book, Treatise on Electricity and Magnetism, Maxwell said the following: of these four different assumptions, that of Ampere is undoubtedly the best, since it is the only one which makes the force on the two elements not only equal and opposite, but along the straight line which connects them. Ampere knew Grassman, but didn't like it. He did prefer Ampere explicitly, Maxwell even created a force law of his own, which I will not present here, which has also this Faraday property of internal tension and so on, internal torque and so on. Maxwell made a general assessment of Ampere's work, also in the treatise. The experimental investigation by which Ampere established the laws of the mechanical action between electric currents is one of the most brilliant achievements in science. The whole theory and experiment seems as if it had leaped, full-grown and full-armed, from the brain of the Newton of electricity. It is perfect in form and unassailable in accuracy, and it is summed up in a formula, this one here, from which all the phenomena may be deduced, and which must always remain the most important formula of electrodynamics. This is Maxwell in the treatise. Despite these extremely strong words, which I never saw him say, praising someone so highly as in this case, this expression here we don't find in any textbooks of physics for 100 years.
And so how did Maxwell treat this? Did he use Ampere's
Yes, yes.
in his whole?
Yes, yes, of course.
Because he said he also created his own variant of it.
Yes, but for the force between current elements, just out of curiosity. But he never worked with them. Which also, when you integrate, you get the same as Ampere and Grassman. But not for two current elements, just out of curiosity. But he just dropped them, just out as a mathematical curiosity for Maxwell. When Maxwell did work with the equations, he did utilize this one here to integrate and so on and so on and so on. So, despite these statements, Ampere's force between current elements disappeared from the textbooks. My own interpretation, why did it happen? That's myself, André. You may disagree, okay? I, André, believe that the main reason for this fact is that modern electromagnetic theory is based not only on Maxwell's equations, but also on Lorentz force law, which is compatible with Einstein's theory of relativity. Beginning with Lorentz force law, we deduce only Grassman's force, but not Ampere's force. The theory on which I work is the other one, which is Weber. Beginning with Weber, we deduce only Ampere's force between current elements, but not Grassman. Okay? I will talk about Weber tomorrow. Okay? But here is the essence. This is Grassman, okay? IDL cross magnetic field. So Lorentz is essentially QV instead of IDL. Essentially that. Okay? If you say, instead of IDL, I will write QV. So, or it came 50 years after Grassman. But if we begin with that, you get that, and then you get integral Ampere, you get the integral form of Ampere, not the force between current elements of Ampere. Weber, on the other hand, that's the expression by Weber. When you calculate the force between two current elements, you get that. Because Weber created his force law to deduce this. Okay, it's very different. Completely different. Tomorrow we'll talk about this, okay? But that's the reason why I believe Ampere's force disappeared from the textbooks. Because it's not compatible with Lorentz. You cannot deduce Ampere's force from Lorentz. Only Grassman. So to avoid questions from the students, you present only Lorentz and Grassman. Because otherwise, why forget Ampere? It follows action and reaction. It came from the great Ampere, and so on, and so on, and so on. So, and most people nowadays They don't even know about Ampere. So how can they answer if the students make a question like that?
But why do people choose to talk about Laurent force instead of Weber electrodynamics?
I'll talk about this tomorrow. So, these two books you can give a look. They are my homepage. So give a look this one later on. It's 500 books. Half of it is the translation of Ampere, complete, of his first paper, 1820, and of his master book, 1826. Okay? And the other half is the history, how he got his force law between current elements. This book, another co-author, Bueno, it's a different subject. It's a comparison between Ampere and Grassman. Okay? Integrations and so on and so on. So, Ampere's electrodynamics is extremely powerful. In the last few years, there has been a renewed interest in Ampere's electrodynamics due to novel experiments and new theoretical developments. Thank you.
Curious about two things. First, you started saying that Coulomb had this 1/r² law, right?
Let me put it here.
For repulsion of electric charge of attraction.
Yes.
How did he do the experiment?
With charges, he did charge two balls, and one of them was fixed in the laboratory, the other one was in his torsion balance. So one was fixed, the other was from a pendulum, torsion pendulum experiment, and it could turn. And by measuring the angle and so on, and varying the amount of charge, and he could deduce experimentally this expression here.
But my question is how did he vary the amount of charge? Because this charge, I don't know, the voltage, the battery was after that, right? Or before that? The battery invention of the battery.
Battery was, yes, but you could charge that by friction, electrostatic machines. These electrostatic machines was known before.
But how do they, but they had a way to, how is it, an idea how much charge there was?
No, that's a good point. Coulomb never tested the proportionality between Q1, Q2. He only tested the variation with the distance.
Vary the distance and then
Yes, that's a very good point. He never tested that. And he said that that was unnecessary, which is not the case. The same with magnets. He only changed the distance. And with magnets he had two, even with charge he had two kinds of experiments and so on. But essentially he was interested only in the variation with the distance. The numerator, he assumed that. That's a very, very good point, which usually it's not discussed in the textbooks, but it's crucial.
A second question is related to that one, because you're saying about currents, right? I imagine that in the beginning of the 19th century, right, people do not know exactly what was flowing the wire, right?
Yes.
Because they had a battery, but
Exactly. They didn't know about that because Volta is the first battery is 18, and Oersted 20 years later. Ampere. And you see, that very complicated force law by Ampere. The law of Ohm, it's very simple. This is from 1826, after Ampere. Very simple law, came only after Ampere. You see, Ampere was, how could he deduce such a complicated law? That's fascinating. But you are right. So people didn't know what was a current. For some people, it had nothing to do with charge. It was like a polarization of something, and so on and so on. So Even as I will take tomorrow, that was one of the assumptions by Weber. How could he deduce that? He said, well, current is charge in motion. So here we must have V1, V2. You see, that's not everyone at that time did accept that. Because for some, a current in a battery had nothing to do with charge. It was a fluid, something. So
Further questions?
Is there an experiment to check the Weber's force?
I will talk about some tomorrow.
Have you tried to find another mathematical formulation which implies the Ampere's force, which is different from...
There is one, even at Weber's time, there is one by Gauss, for instance. Gauss did work together with Weber in Göttingen. So Gauss had another force law between point charge different from Weber's, in which he could also deduce Ampere's law. But Gauss' law could not conserve energy, and Gauss' law could not deduce Faraday's law of induction. So it was discarded, essentially. But there are other expressions which can lead to Ampere's force between current elements. Weber's not the only one.